planet and brown dwarfs at wide orbits. You have to. Copy.
Okay, so can you hear me? Okay. So I'm here to present you the results of the NACO large program, which is a direct imaging program that we have done with NACO at the VLT. And I'm presenting all these results on behalf of the long list of people which is here. So, well, I won't go into much detail for the scientific context because it has already been presented very precisely by other people this morning. Just I will say that this project started in 2008, 2009, and at the time there were few large surveys. And of course, the picture has significantly changed in the recent years with surveys targeting different types of stars, such as very massive stars, early type stars, or M stars. And of course, with the new surveys that are going to be in the upcoming months or years, and some of them you've heard about today. And so the scientific goals of the NACO LP program were multiple. The primary one was, of course, to measure the occurrence of planets and brown dwarfs at wide orbits in the 50 to 500 AU range. But also it was designed to be a preparation for the sphere near-infrared surveys, in particular for the identification to have a first epoch for the contaminants around some of the sphere targets. And of course, a bonus would be the characterization of any new substellar companion. Okay, so in terms of sample, the initial selection was made from the sphere near-sur database, so the near-infrared survey. And with these cuts in terms of distance within 100 parsec and in age below 200 megayears. We also applied a cut on the R magnitude. This was primarily designed to ensure that the targets will also be observable with sphere in the future. Of course, all the binaries, either spectroscopic or visual within 6 arcseconds, were removed from the sample, and we applied some color cuts to select mostly FGK stars. So we ended up with about 200 targets, and by cross-correlating with previous and as well as ongoing surveys at the time, there is a beginning of list here, we ended up with 110 stars which had never been previously observed at high contrast. And so in terms of sample, you can see the distribution in age and spectral type. So the hashed area is the observed sample, and the blue distribution is the full 200 star sample. And you can see that in spectral type and age, we have pretty much a scaling of the observed sample with respect to the full sample. But for the distance, we actually focused on targets which were at slightly farther separations rather than closer separations, which were previously targeted by other surveys. Okay, so for the observations, we had a total of about 18 nights. 13 of them were dedicated for the search of candidates, so the first epoch, and we then had 5 nights of follow-up. The observing strategy was to observe in H band with a field of view of 14 by 14 arcseconds. To have a proper sampling, and to use the pupil tracking mode of NACO to have a proper implementation of the angular differential imaging. And we started the observations with the LIAU coronagraph, for which you can have an illustration here. But unfortunately, we discovered a problem with the pupil tracking mode of NACO. And basically what happened was that the star was drifting by several pixels per minute behind the coronagraph. So we actually had to switch to a different strategy and use saturated imaging, but this implied to use smaller dits and then to do some shift and add to compensate for the shift. Of course, for the different observing runs, we had different sets of important calibration. The most important is the astrometric calibration that we perform at each observing run, but then we had some other basic calibrations to ensure that we could get the most out of our data in the end. Okay, for the analysis, since it was a multi-institute project, we had actually 4 almost totally independent pipelines. And 2 of them were actually used to analyze the complete set of data of the program. And so I won't go into much details, but the general scheme was to do first some cleaning, then some frame recentering with different methods when available, then some frame rejection to remove when the AO loop was open, for instance, or when the weather was really, really bad, and then the ADI analysis parts. And so for the results that I'm going to present here, the analysis was done with low-key within 3 arc seconds. You have an example here, and then some simple spatial filtering for larger separation. Here, an example of a filtered image, and the combination of both for the final image. And for some of the targets, we had to use some temporal binning to reduce the number of frames to speed up the analysis. Okay, for the detection limits, they were estimated in a very classic way using azimuthal RMS in a lambda over D analy, normalized to the reference PSF, so the PSF without the coronagraph or unsaturated. And of course, the ADI flux losses and the smearing because of the rotation was compensated by introducing fake planets, fake objects into the data at different orientations. And this is I would say, the envelope of detection limits, with the worst one here, the best one, and our median detection limit. For the identification of companions or candidates, actually during the observation, we immediately rejected the obvious binaries. And so we actually discovered 17 previously unknown binaries, because at the beginning we had already removed all the binaries that we could. Then the candidates, companion candidates identification was done by eye inside the final images, and sometimes relying on the detection map. And we based then our follow-up based on observability of the star, its proper motion to ensure that we could rule out any background companion, and the mass and physical separation if the candidate was actually bound to the star. And sometimes we also relied for a priority rank on the Besançon galactic models. Okay, unfortunately, we didn't discover any new substellar companion. And here you have a typical example where all the candidates within of the first epoch follow the path where you would expect them for background objects at the second epoch. Okay, so even though we didn't discover any new substellar companion, we had some interesting results. The first one was this debris disk around HD 61005. Actually, this was already known from HST images. It was known that it had a very peculiar geometry with asymmetric brightness. And actually, we resolved it for the first time as a ring with NACO. And here you have our ADI analysis with where you can really see the ring here with the gap inside and some streamers here. And what we discovered is actually a very small offset between the star and the center of the disk, which is about 3 AU. That was our estimation. And this could be the indication of a planetary companion. Of course, we ruled out very massive companions from our NACO observations, but actually a very small eccentric planet could be the origin of this small offset. Okay. The second result, interesting one, was the false positive around the star HD 8049. It's quite interesting because originally we discovered a bound companion to that star, and originally the age of the star was estimated to be between 100 and 400 megayears from stellar activity in age indicators. And so they were primary young estimations. But actually, after some further analysis, we discovered that other age indicators were actually more compatible with a much older star. In particular, the lithium and the galactic motion suggested a very much older star. And so there was some kind of contradiction, and we also had some radial velocity trend, which was actually only compatible with a more massive objects, possibly a white dwarf. And actually, the white dwarf was later confirmed with symphony spectroscopy with a typical spectrum for a white dwarf. And actually, our interpretation is that the central star here accreted some material from the white dwarf progenitor, which increased its stellar rotation, and which led to the estimation of a young star. So it mimicked a much younger star. Okay, so as I said, we didn't detect any companion, but you've heard since this morning that we can still have some interesting results from statistical analysis using the null results. So we used Monte Carlo simulations to generate a lot of planets on a mass, on a grid and semi-major axis, mass semi-major axis grid with other random orbital parameters. Then we check the detectability of these simulated planets against the observed detection limits to generate a probability of detection map for each of the targets. Of course, this analysis is completely model dependent because we have to rely on evolutionary models to convert the observed detection limits into mass and semi-major axis. But okay, so here you have a typical example where we have generated a lot of planets, and these ones, of course, are considered as detected, while these ones are not. Okay, so when we do that for all the targets, all our observed sample, we obtain here our mean probability of detection. So you can see that we are quite sensitive below 15 Jupiter masses within the planetary mass domain. And when we convert that into an upper limit to the fraction of stars with planets, we can estimate that less than 20% of stars have planets heavier than 4 Jupiter masses within a certain range, which is about 50 to 800 AUs. Another type of analysis that we can do is that assuming some mass and semi-major axis distributions, for instance, from radial velocities, such as the Cumming et al. Distributions, which found these power laws for the mass and semi-major axis distribution, and also assuming that there is some cutoff in semi-major axis above which the planets could not form, we can set some constraints on, for instance, this cutoff in semi-major axis. And so if we consider our Monte Carlo simulations for different values of this beta parameter and alpha, for instance, for the Cumming et al. Here, we can say that the cutoff with quite good confidence that the cutoff must be below 75 AU. Okay, so this is for our observed sample of about 60 stars. But actually, when you combine that for the full sample of almost 200 stars, you can set even tighter constraints. And in that case, the range below which 20% of stars have planets less heavier, don't have. Okay, so this range is between 20 and 1300 AU. And then we can say with good confidence that the cutoff must be below 24 AU. And so what's interesting in this preliminary analysis is that it's compatible with previous analysis so far. So it's a good indication that we are on the right way. Another analysis that has been led by people in Zurich is to use a combination is to assume that planets and brown dwarf have actually distributions that may overlap in certain range of parameters. And so by assuming different distribution for both the brown dwarf and planets, they also do some kind of Monte Carlo analysis and to generate different populations. And this is what they measure for this is the number of detections they would expect from the NACO large program. And actually the probability of having a null detection, so here is about 7%. Of course, this is only for one set of parameters, and they are currently in the process of doing a much wider parameter space analysis. Okay, so in terms of ongoing work, we have almost concluded the analysis of all the stellar parameters. We are in the process of publishing the results of the observed survey. And for the statistical analysis, it's also in good progress. We are extending the analysis to include other evolutionary models, but we also plan to include physical consideration, in particular to test core accretion or gravitational instability models, such as already been done, for instance, in the study by Johnson or Rameau previously, and to have to try to link our statistical analysis to physical constraints. Okay, so the conclusions, I remind the science conclusions here, but I'm just going to insist that we've learned a lot of lessons for the future, in particular for the SPHERE survey, because this survey was designed mostly by people involved in SPHERE. In particular, we have learned a lot in stellar properties determination and age diagnostics. We've now a very quite strong calibration strategy. We've done a lot of work of algorithm and testing and comparison, and we've also also worked on false alarm determination, but most of all, we've learned to work together for this future huge survey that we're going to do with Sphere. And I think it's a very important aspect. Okay, I'm just going to advertise once again the DIVA archive that we are trying to set up, which has already some surveys included. Here is not the full list, but we have about half a dozen of them. And it's going to become public very soon, hopefully. So if you want to contribute and send your already published data, it will be most welcome, and it will be a contribution to the whole community. Thank you.
Thank you, Arthur. Questions? Laird, can you have the mic down here, please?
So thank you for that talk. One of the things that I think we're going to hear a lot about, and most of us worry about quite a bit, are stellar ages. And I was very interested in that one example. Can you speak a little bit about how you found that the geochronology age was actually, it looks actually quite like a young object there, but in fact, it's obviously much older. And what was the rationale? Is that because it actually had a companion, there was a spin-up?
So yeah, we discovered the companion, and so we thought, wow, that's great. We finally have some brown dwarf in that sample, but then we had to do some further analysis, and actually the person working on the age estimations and did some further analysis and noticed that there was some incompatibility between the different age indicators. So of course, maybe this should have been a work done beforehand, but of course, when you have a large sample, it's difficult to have everything consistently, and this is the discovery of something interesting that triggered further analysis, and in the end, it proved to be something else that we hoped.
I guess the interesting thing is it possible that perhaps some of the age indicators are actually skewed to looking younger if they have, companions that are non-substellar, and that would be an interesting skew in the literature. Anyways.
Stan Metchev, Stony Brook University. You mentioned that you made an effort to exclude all stars that were previously observed at high contrast. So your sample is of stars that have not been observed before, so 110 stars, which is obviously a great thing to do. We don't want to duplicate use of resources. I do worry a little bit of what kind of unknown biases that might introduce, however. And in particular, the way I think there may be some bias is that you have a sample of 110 stars you observe very deeply, and you find no brown dwarf companions. Whereas there's been at least 2 or 3 different surveys that will find a frequency of 3 to 4%. So your result seems very significant, but I wonder to what extent you may have actually taken account of all the biases in your selection.
Okay. Well, so the idea, the original selection was without excluding anything, and with these cuts on the different parameters, and then it's only by cross-correlating with stars that had already been observed that we removed pretty much 90 stars. So I think the original sample here is probably, well, we tried to do it as unbiased as possible. But
so just to quickly follow up, if you take all 200 stars, do any of them have any known brown dwarf companions?
I think some of them do, yeah, it's possible.
So maybe that's the statistical analysis that will need to be done.
Yeah. Mm-hmm.
One last question.
Jay Farhi, University of Cambridge. I'd urge you to seek other explanations for the possible mismatch between your age and activity relation, because I'm skeptical that this exchange of mass and spin-up is possible. There are many systems with white dwarfs with a low mass main sequence companion that are much closer than 50 AU, and they've accreted essentially nothing during the AGB and giant phases. And with your thing so distant, I doubt it's even possible to do anything whatsoever to spin up a star like that.
Okay, thank you. That's
Okay,
interesting.
let's thank Arthur again.